Okay then, today being the 27th, we have a review day. Wow, I did not notice that the exam is on April the 1st. Appropriate. Maybe. Boy, I could put all kinds of different stuff on that exam now, couldn't I? But, no. Not do that. Of course, your answers might be just as creative. So, it is the case that if you do not take the test on Wednesday, you can take it later in the math lab up until the following Tuesday. So that's an option. But what I want us to do now is to go through the review that I put out here for test number 3. Starting here on page 392. So what we're dealing with here, first of all, we have to know what kind of problem this is. Katie, can you tell me what kind of problem this is? Page 392, number 5.
Yep. We are dealing with the confidence interval true mean. Population mean.
Okay, the confidence interval for the population mean. What's that formula?
Is it the x bar minus t alpha over 2, parentheses s over square root of n?
That's correct. And then that is the lower limit for the mean, and then the upper limit has the plus side.
Yep.
So the confidence interval for the mean. And so then we need to know what these symbols actually are. Joseph, can you tell me what these symbols actually stand for?
Your x bar is your mean.
This is the mean of the sample. Okay, the sample mean. All right.
Your t is your score that you're going to be. You find that on your table.
Okay, so this comes from the table.
N is your number of population, or the number of your sample population.
Okay. You're using the word population, but I don't think that it means what you think it means. All right. Sample
The number of the people that you sample.
is the number of people that you sample. There's no such thing as a sample population. Okay? A sample is a sample. A population is a population. Population is everybody. A sample is taken out of there. So what you want is sample size. Okay, that's N. And then this letter S. Standard deviation. This is the sample standard deviation. Okay. Now, for this particular problem, all we have are the data numbers. But on the test, I would give you the actual mean and standard deviation. Okay, so you'll know that. And so then, if we look at this, working with that particular thing, not there. Notes of activities, I would think. All right, so then what we need is the mean and the standard deviation of our data set in order to come up with the answer here. Okay. Todd, do you have that mean and standard deviation for this?
Yeah, I have 83.45 for the sample mean.
83.45, see? Okay.
And then the standard deviation is 8.43.
Standard deviation of 8.43.
All right. So it is good that these things are reasonable, okay? So that when you look at the actual data, you say, okay, that makes sense to have that be mean and standard deviation, okay? So then when we put those numbers in there, hopefully we get the answer, 76.9 on the low end, 88.3 on the high end. But we need to know how to find that t. So, Alex, can you tell me how to find t in this situation?
So you go to table F,
Okay, so we're at table F, that's correct.
and go to your 95%.
Okay, we're looking at the column where it says 95% confidence interval, all right.
And it is going to be there's 11 sample, or there's 11 data values in the sample.
That's correct, 11 data values in the
So
sample.
you go n minus 1, then you go to 10.
So we're going to use degrees of freedom of 10.
Which is 2.228.
2.228, all right. Now, then we have to know what is the purpose of the confidence interval. April, can you tell me the purpose of the confidence interval?
To measure something with specific confidence.
Okay, to measure something about a population with specific confidence, okay? The word population needs to be in there because that's what we care about here. What are we actually measuring? Somebody tell me what we're actually measuring here.
The length of children's animated films.
Okay, the length of children's animated films. So this is an important part of these problems, okay, is that you don't just get the numbers, but you know what they're telling you. Okay? So what this is telling us is that children's animated films, the average length is somewhere between 77 and 88 minutes. We came up with a sample mean of about 83, but the actual value for the population is somewhere between 77 and 88. Now, you would certainly want to know this if, for example, you're running a television station and you're going to put on these animated films. You want to know, well, what can I expect on average? And this will tell you the average. It doesn't tell you what to expect in terms of necessarily each individual film, but it tells you where the average will be located, somewhere in there. Okay. So that is confidence interval for the mean. Now we look at number 8 on this same page. Sarah, what are we talking about for number 8?
The U.S. Travel Data Survey of adults that responded to the favor of historical sites for vacation.
Okay, so people favor historical sites for vacations, right? So that's what we're measuring. So then what is this problem asking us for, Sarah?
Mean again? No.
Okay, so yeah, we have to ask the question, how do we know? How do we know what we're looking for? Okay. Alex, can you explain how we know what to look for number 8? Okay. Lee, can you tell me how I know what to look for number 8? What kind of a problem is it? How do I know?
It's for, you're looking for the population proportion.
Okay, how do I know I'm looking for proportion?
It says so right there.
Okay, that's one thing. Find the confidence interval for the proportion. Okay, that's one reason why. Okay, another reason why is that I think about what's being measured. I'm not asking the question, how much time do they spend on their vacation? I'm not asking the question, how much money they spend. Or what the question is dealing with is the percent of people saying that they want to go to a certain place. Okay? So when we're talking about proportions, we're asking a question and it's either a yes or no answer. It's like the binomial situation we were talking about. How many successes out of the total? Okay? So, Fritz, can you tell me the formula for confidence interval for a proportion?
Still exploring it.
Nope, not explorer. Todd, can you tell me the formula?
P hat minus Z alpha over 2 square root of P hat Q hat over N.
Okay.
Yeah,
And then on the other side, we would have the plus.
yes.
Okay, confidence interval for proportion. And so what we're dealing with here is, we ask a certain number of people and a certain proportion said yes. So, Todd, what number do I actually put in here for p hat?
P hat is 0.42.
Okay, so I make this a decimal number, 0.42. And Q hat, what would that be, Tom?
1.96.
Oops, you gave me the
Oh,
thing
oh, okay.
a little early there.
0.58.
0.58 is Q hat because it's 1 minus P hat. And then you want this to be 1.96 right here. Okay. So, April, where do we find that 1.96?
On our table, up under 95 and under the score.
Okay, so we're looking at 95% confidence interval. We go all the way down to the bottom where it's talking about Z-scores, and that's the number that goes right here. And then N is the sample size, in this case 1,500. All right, so Katie, can you describe for me how we would say the answer to this problem in words?
The long way, the summary, or?
No, just tell me what it is. What's that answer in words?
Proportion is,
What proportion?
the population proportion?
The population proportion of,
Okay, hold on now.
okay,
Population proportion of adults who favor visiting historical sites for vacations is between 40 and 45%.
that's correct. Okay, so the proportion of adults who like historical sites on vacation is, the population proportion of that is between 40 and 45%. Great. That will work. So, again, there is this important thing that you can look at the problem and know what kind of a thing it's asking for and what formula in order to make that happen. Right? So, Joseph, what about number 12 here on this page, 392?
The equation, or
I want to know what kind of problem it is.
you find what the sample size would be.
Okay, so this is a sample size problem. Okay. So, Alex, can you tell me what the formula we're going to use for sample size calculation?
N equals P hat, Q hat, parentheses, Z alpha divided by 2 all over E and parentheses.
All right, that's it. Now it's important for you to recognize what is that Z with the alpha divided by 2 on it. The alpha divided by 2 is a label telling us which Z-score we want, and we find that just what we did the last time by looking that up on the table. So we have a Z-score using alpha divided by 2. And that's the one that we look up for the confidence interval, which once again, 95% confidence, 1.96. And that little chart will be given to you, I mean that table F thing will be given to you. Now, again, P hat and Q hat come from this when it says the survey found 73%. So you'd have 0.73 here, 0.27 here. But then the question is, what do we use for E? So Lee, can you tell me what we use for capital E in this problem, number 12?
That would be 0.03.
And where does that come from in the problem?
Within 3 percentage points.
Okay, within 3 percentage points. So what that's saying is a margin of error of 3%. And so that translates into a decimal number. Really important that you have that as a decimal number, else it's really wrong. Okay? So then when you put that in there, you'll come up with the 842 number. And then if we do not have previous information, then we use 0.5 in here for both. Okay. All right, we're just setting them up and knocking them down here, I think. So if we get done way early, I guess that's okay. I suppose. As Joseph has told me, I should contain my excitement. So I will try to do that.
Bubbling over it.
I know it. So now we're on number 13. So, Sarah, what kind of problem is number 13?
Population standard deviation.
Population standard deviation. And it is the confidence interval for that. So that's what we're going to use. All right. Nikki, you have the formula for confidence interval for standard deviation?
I think so.
Okay.
Is this the square root over n? Okay, yeah. Square root of n minus 1
Okay.
times s squared over. Hang on, I got it. Pi
That's
squared.
right. Yep.
Right.
There we go. It's there. Chi-squared right. And then,
And then you do left.
same thing with chi-squared left. Okay. Now all we have to do is find these. Okay. So, April, how am I going to find these chi-squared numbers?
I do 1 minus 0.95 divided by 2.
Okay, so 1 minus 0.95 is 0.05, and then 0.05 divided by 2 is 0.025. So this, when we're talking about the confidence interval, this was a 95% confidence interval. That's what's being asked for. So then, if it's a 95% confidence interval, this is alpha, and this is alpha divided by 2. What I normally do if I have chi-squared is I'm going to draw a picture of something like this. All right? So, Katie, can you tell me where to find these numbers?
The chi-squared right, we would look on table G,
Okay.
and we would look under the 0.025.
All right.
We would take the degrees of freedom, which would be 17,
Okay, so what you're saying is the sample size is 18.
minus 1.
So then degrees of freedom is 17. Okay, then what do we find when we look at
30.191, and that would be on the right side.
Okay, so 30.191 is chi-squared right.
And then it'd be 0.975 for the left.
Okay, so then this one we directly look at alpha divided by 2. That gives us chi-squared right. Over here then we need 1 minus that number. So it's 0.975, that's what we're looking under.
and that's 7.564.
All right, so the process of finding these numbers when you're doing the confidence interval for a standard deviation, you look at how much confidence you have, in this case 95%. 1 minus 0.95 tells you alpha, so alpha is 0.05. Divided by 2, that tells you the area in the right tail. So you're looking up that area on the table. Now it is confusing. This textbook actually calls that alpha out there, but it's really alpha divided by 2 in this situation. They should have just said area. The area is 0.025, so we look up that. That gives us on the right. And then when you're looking at the chi-square table, you see how it's broken into two sections. You have the chi-squared right numbers, and then the chi-squared left, and they reflect each other. So you've got 0.01, 0.99, 0.025, 0.975. So that's how we get the other side. Look up those numbers, put them in, make it happen. Standard deviation. Okay. And so we need to be aware of the fact that when we have this, the sample standard deviation is 0.29. So if the sample standard deviation is 0.29, the numbers we come up with down here, one of them is less than that, one of them is greater than that. So this is 0.218. This is 0.435. Okay. Now, Joseph, can you tell me what is the meaning of these two numbers?
This is where the percentage of confidence you would say that the standard deviation should fall within.
Okay, one word missing, the population standard deviation, okay? The population standard deviation is between these two numbers. And we know that with 95% confidence. This number, this number is 0.29. That came from the sample. We know that's not true. The actual value of the population is somewhere between 0.22, 0.44, or less. Okay? All right. So yeah, confidence intervals, once you figure out what kind of problem it is and what formula to use, they don't take that much time, except maybe for this one, for standard deviation, a little bit more complicated. So then, Alex, are confidence intervals designed to give information about the population or about the sample? No. Sorry. April?
Population?
The population, okay? The purpose of the confidence interval is to measure something about a population with a specific amount of confidence. You'll see that definition on the test, so it'd probably be a good idea for you to have that memorized. The purpose of a confidence interval is to find a measurement of the population with a specific amount of confidence. Okay. I don't know if I like question number 6 anymore. But we'll just talk about it and then we'll ignore it. How about that? That seems reasonable. If I'm talking about the confidence interval for the mean, I have this, x bar, and then minus t of alpha over 2 times s over the square root of it. And then positive. This thing right here, this plus and minus, that we can call the error term. That's the amount of difference that we might have in the actual population standard or population mean. So if we say, I don't know what the population mean is, but I think it's within this interval, this is the, in a sense, the width of the interval. Okay? This, and then same thing on the other side. Now if I ask the question, what would change that?
Confidence interval.
Okay, this right here, if I change the amount of confidence, that would change the size of that interval. Right? We talked about that. That if you want more confidence in your results, then that means that this would have to be bigger, so you'd have a larger interval. That makes you more confident because you can hit it with the bigger hammer kind of thing. Okay? What about sample size? If you have a large sample size, what happens? You get a more accurate interval. Okay, the larger the sample size, the smaller this thing is going to be. So then your answers will be more accurate. What about the standard deviation? What if your data has a large standard deviation? What would happen to that interval? It would have to be bigger. The larger the standard deviation is, and it's on top of this fraction, the bigger that interval has to be. So if your data is crazy, then you're not going to have a very accurate idea of where the average is. Makes sense. But let's ignore that question now that we've gone through it. Why somebody would put that on their practice test, I have no idea. So let's get rid of that question. And it renumbered. How about that? Fancy computer stuff. So now we have a new question 6, which is on page 461, so that's where we're going to go. Now, I do want you to understand what this is going to look like on the test when we get to the concept of hypothesis testing. Okay? The problems that you had on your homework, I would give you a homework question, you would do the whole thing, all right? But that's not how most of the test is going to be, right? Most of the test is going to be problems broken into pieces. For example, I'll give you the problem, and I will say, tell me the null and alternative hypotheses for this problem. You write that down, that would be one question. Then I have another one. I give you the problem, I give you the null and alternative hypotheses, I say, find the critical value in the rejection region. Find that, that would be a different question. Then I give you a problem, I give you the information from the problem, I say find the test value. That would be a different question. Then I'll have a problem where I say here is the test value, here is the critical value, what decision do you need to make? That would be a separate question. Then I have, here is a problem, here I decided to reject the null hypothesis, summarize that conclusion, and that would be a separate problem. And then I'll have another one. Here's a problem, here's all the information, and I say do not reject the null hypothesis. Tell me the summary of that conclusion, right?
So, for example, if you say that, should we say the short answer of no decision, or we have to go through?
That would be correct. Short answer for that situation would be no decision. Okay? So there will be times that I will say, give me the short answer. But there will also be times when I will say, give me the long answer. Which means you're given that sheet that has all the different parts of the conclusion. You need to fill all that out for that particular thing. Okay?
Are we gonna have, can we have that sheet?
The sheet
right
is
now?
printed on the test,
Oh.
yes it is. Okay? All right, because of course, if I just said to you, do a problem, and you got it wrong at the beginning, then that would propagate throughout the whole problem, right? So I only put one of those on there. It's not the whole test, but yes, you will have one problem where I will say, here's the problem, do the whole thing. So then you have to come up with the hypotheses, the critical value, the rejection region, the test value, the decision to make, and the summary of the conclusion. That will be one of the problems. And it'll be worth more than just 5 points, okay? Because you'll have a lot of stuff going on.
And there's only one like that?
There's only one like that, correct?
And what kind is it going to be? Is it going to be a lead?
Well, no, that would be telling. No, I have my little secrets. Yes, that's true. All right, so what we have here then are examples of hypothesis testing. So when we do hypothesis testing, you should have the sheet about hypothesis testing. You should have that in front of you. You should not allow it to get covered up by anything else, because you have to be able to follow that process all the way through to the end. Okay. So here we are, page 461, number 10. And we are asking the question, what kind of a problem is this? All right, so Sarah, tell me what kind of a problem is this one?
A proportion.
Okay, this has to do with proportions. So this is a hypothesis test for proportions. Now I gave you this sheet about the different kinds of things that are out there. So the question that we have to ask here, is this a situation where we have two different samples? Or is this something where we just have one sample compared to a number?
One sample.
Okay, one sample compared to a number is what we have here. Right? So, Todd, can you tell me what my hypotheses will look like?
Then the null is P equal to 60.2.
Okay, so P would be equal to...
And P
I don't like 60.2 necessarily.
So then it's 0.602.
0.602, there we go.
I do the 60.2, I still get the same answer.
If you do 60.2%, And then when you actually do the calculations, you change it to this. That's okay. So in the calculations, you have to use the decimal, 0.602. If you put 60.2 on there for a hypothesis, that's okay. As long as when you put it into the test value, that you're using 0.602, all right. Joseph, what's the alternative hypothesis?
The alternative would be that it's greater than the null or greater than point.
Okay, so what am I going to write down?
P greater than 0.062.
Okay. So the hypothesis is a statement about a number. Okay. All right, so far. What's our next step, Joseph?
Next step is to find the critical value and rejection rate.
Okay, so I need my critical value and rejection region. Joseph, where am I going to look for that? Table F. And where on table F are we going to find it? Okay, so it's 1 tail 0.05. What's that number?
1.645.
Okay. And that's going to look like this. Z-scores have 0 in the middle. 1.645 is out here. We would shade that in. That's alpha of 0.05. One-tailed test. Okay. Katie, can you describe for me a situation where I would want a negative number for my critical value and my rejection region?
Yeah, it's less than.
If that had been a less than symbol, then I'd go with negative numbers, all right? So, Katie, what do I need to do next?
Find the test value.
My test value, and what's my formula for that?
Z equals P hat minus P divided by square root P cubed over 10.
Okay. And where does the P hat come from, Katie?
The information that we had, the 206 x over n, so 260 and make over 400.
Okay, so P hat comes from the sample. And so we get a number there. Looks like it's going to be 0.65. Okay. April, what's P in the test statistic?
0.602.
Okay, 0.602. That comes from the null hypothesis. So P hat comes from the sample. P comes from the null hypothesis. Put all those in there. Crunch all those numbers. Q is 1 minus P. And we get test statistic of 1.96. Critical value is 1.645. And I have here that I would reject the null hypothesis. Lee, why would I reject the null hypothesis?
Because it's within the critical region.
Okay, the test value is in the rejection region. Okay, a little different than what you said. Okay, test value is in the rejection region. So we reject the null hypothesis. Now, Lee, can you tell me what my conclusion is if I reject the null hypothesis?
The long way.
No, give me the short answer.
There is evidence, so we are accepting the alternative.
Okay, unfortunately what you're telling me are statistics words. What I want are problem words. Okay, for this particular problem, what is the conclusion? Okay, Nikki, can you tell me what is the conclusion of this particular problem?
That there is not more than 60.2% of inmates for drug offenses?
Actually, no. We reject the null hypothesis. If we reject the null hypothesis,
So there is.
we prove the alternative. Okay? So when I say this thing is way out here, what I'm saying is the true proportion is greater. So when we say reject the null hypothesis, it is very important you know what that means. That we prove the alternative. Because that's the entire point of the problem. Okay? If we reject the null hypothesis, we prove the alternative. And so then, if this is true, now we need to say what that is. All right, Nikki, you want another chance on that, maybe?
Do you want the long version?
No, I want the short version.
That there is more than 62% of inmates.
Okay. When we're looking at the answer, we have to look at who's asking the question and why do they want to know it.
Oh, that the warden is correct.
Okay. What is he correct about?
Hypothesis is correct, that there are more than 60.2% of inmates with drug offenses
In his prison.
in his prison.
Okay. He doesn't care about the general public. He's looking at his particular prison. He wants to know if the percent at his prison is higher than the national percent. Okay, that's what he's looking for. Right? Does that make sense, Nikki, what we're saying? Okay. So, it's just, I understand this is kind of new, but it's really, I mean, the point is, we want to make a decision, right? We want to make a decision. We want to make a data-driven decision. And we have to look at the problem to tell us what that decision actually is. The numbers. I mean, wonderful, yes. Great to know what the numbers are. But the question is, what is this person looking for? And did they find it? They're concerned about their particular prison. They want to know, is this percent here more than it is expected from the nationwide surveys? And the answer is yes. Okay? Now, how do we get that from the long version of the conclusion? With 95% confidence, there is evidence. So if there is evidence, that means we've proven something, right? And then, what are we measuring? Okay, the population proportion. And this is where we find out what we're actually talking about. What is this population proportion?
Inmates that are drug offenders.
Inmates that are drug offenders and where did this come from?
The warden's prison.
In this prison, okay? And what direction?
Is greater than?
Greater than. And what are we comparing it to?
National population.
The national proportion. Okay, once you have these pieces in place, then maybe it's more clear exactly what's going on, right? We're trying to measure to see, is the population proportion in this prison greater than it is nationwide? And the answer is yes, there is evidence. Okay? So when we say short answer, I don't want you to think that just saying yes is necessarily the case. I want you to get yes, this thing is true. Right? That's short answer. All right, so that was that one. Let's look at another one. Number 14. Todd, can you tell me what kind of a problem number 14 is?
Standard deviation.
Okay, it's a hypothesis test for standard deviation. Todd, can you tell me what null and alternative hypotheses would be?
So null and the standard deviation equal to 3.4.
Standard deviation equal to 3.4.
And then the alternative is standard deviation larger than 3.4.
Okay, standard deviation greater than 3.4. Okay. Now what we can see is that it is listed here in the problem. It says, can we prove, because they feel like it's 3.4, but what we're going to do is look at the sample and say the sample standard deviation is really telling us the direction of the proof. Okay? We start with this idea, they think it's 3.4, but then we take a sample, and so then that tells us which direction we're trying to prove. So we're trying to prove greater than. And so as I mentioned in the problem, we're going to use one tail, and we're going to use the traditional method. Okay? So, Sarah, what do we need for this?
Define the critical values in these equations.
Okay, so we need a critical value. Where am I going to look for my critical value?
On table F.
Nope, not on table F. Alex, can you tell me where to find the critical value for this problem? I think it's probably safe to say no. Katie, can you tell me where to find the critical value for this problem?
Table G,
Table G. Why do you say table G?
because we're dealing with chi-squared,
Okay, and why are we dealing with chi-square?
standard deviation.
Because the standard deviation. Okay, we're doing a hypothesis test for the standard deviation, so that means we're going to look at the chi-squared table, which is table G.
So we'll look under the alpha,
Okay, so we're going to look under alpha
0.05.
0.05.
And the degrees of freedom is n minus 1, so 24 minus 1 equals 23.
Okay, so we have degrees of freedom is 23.
And we'll get the critical value of 35.4.
So degrees of freedom was 23, alpha was 0.05. So that's what we look up on table G. Because we're doing standard deviation, we're using table G. Now, hopefully, all right, when you look at your equations, which are given to you, all right, when we ask the question, what equation am I using for this, for the test value, that has to be the same place that I look up the critical value, right? So if there's a question, well, which table am I going to use? Well, what are we looking for? We're looking at chi-squared. So I'm not going to look up chi-squared anywhere else. Chi-squared is on table G. Okay. So, April, can you tell me what the formula is for the test value for this?
Chi squared equals n minus 1 s squared over sigma squared.
That's correct. S squared over sigma squared. S is the sample standard deviation. Where does sigma, where do we know where that number is, April?
That's what we're 3.4.
Okay, and it came from the null hypothesis. Okay, S comes from the sample, sigma comes from the null hypothesis. So that's how we know what numbers to put in there. And when we put those numbers in there, we come up with a test value of 35.1. Now these textbook authors are kind of tricky. All right, 35.1 as being a test value compared to 35.172 as a critical value. If this were a standard mathematics class, we would say do not reject the null hypothesis. It's not out far enough. But this is a statistics class, so we say close enough. All right. 35.1 is awful close to 35.172. Okay. Now, unfortunately, this is the example they had in the textbook for me to put on our test review. But generally, I would not do something like this on a test. To make it really be close like this, and you'd have to make that kind of decision. But in reality, okay, when we're talking about is that out there far enough to say that it's out there? And the answer is, yeah, it's out there far enough. Well, okay. If we had Microsoft Excel open here, and if we were to say, well, what is that actual tail out there? And I say chi-squared, inverse, right-tailed. Oh, I just need chi-squared. And so I've got, what, 35.1 degrees of freedom, 23, and true, and we'll do okay. So if we were to actually ask the question, if I go to 35.1, how much of a tail do I have out there? 0.0508. That's awful close to 0.05. Not worth arguing. Okay. So, emotionally, most people aren't ready for this. So just let me say, I'm not going to do this on the test. I'm not going to have a situation where I'm going to say, well, it's really close. Are you going to do that? No, you're going to lose 10 points. That's not what it looks like, right? Generally, on the test, if it's in the rejection region, we reject. Okay? But this is awful close, so we would reject this. So we're going to do one more. Yeah, I think we can do one more, and then we can be done. All right. Okay, so I'm looking at the ag business program versus the welding program. And I asked them, how much time do you spend with meal preparation? Ag business has a mean of 30 minutes. Standard deviation of 10 minutes. And the number of people I talked to was 40. Welding, they had a mean of 25 minutes. Their standard deviation was 8 minutes. And I talked to 36 people. I want to do a hypothesis test in this situation. So, Lee, could you tell me what my null and alternative hypotheses are going to look like in this situation?
HO, A1, A2.
Nope, that's not correct. Am I looking at the number of people out of the total surveyed? No, I am not. Joseph, can you tell me what my alternative or null hypothesis is going to be here? Nope.
Is it mu?
It's mu. Okay? I could compare standard deviations, but I'm not. Okay? Because what I'm really interested in is the averages. Okay? Do ag business people spend more time preparing meals than welding? Okay? So, how do I know that? How do I know this is not a proportion problem? Because I'm not asking the question of these 40 people. I'm not asking a question that has a yes or no answer. I'm finding out how much time they spent. And I'm finding mean and standard deviation. So this is not a proportion problem. Okay. Lee, does that make sense?
Yeah, I didn't see the top.
Okay. All right. So, Tal, what does my mu or what does my H0 look like?
Mu1 equals to mu2.
Okay. And the alternative?
larger than UT.
Okay. And I'm picking the ag business to be sample number 1, welding to be sample number 2. I could have picked it to go the other direction. Doesn't matter as long as I'm consistent. Okay, so this is my null alternative hypothesis. Fritz, what do I need next after I get my null and alternative hypothesis?
Find the critical values from the appropriate table.
Okay, so I need to find critical values from the appropriate table. Sarah, can you tell me what the appropriate table is?
Is it G?
No, it's not. Okay. Joseph, can you tell me why it's not table G?
Table F.
Why is table F?
T score.
Okay, why are we using T-score?
Is that what our equation tells us?
Okay. We're using T-scores. We were talking about using averages. Are interested in the relation of averages. That means we're going to use T-score. All right, Sarah, does that make sense?
Yes.
Okay, so we're looking at table F. Alex, can you tell me where on table F I'm going to look?
Yeah.
Where does it show the confidence?
Yeah.
What confidence level?
Okay, that's the completely appropriate question right here. How much confidence are we going to have? Normally, if it's not given to you, you would say alpha is 0.05. Okay, so I have alpha 0.05. So, Alex, tell me what else I need to know.
For some, for confidence intervals.
No, this is not a confidence interval. That's not going to give us what we need. April, can you tell me? Okay, what degrees of freedom am I going to use here?
35.
Why would I use 35 degrees of freedom? Okay, I use the smaller sample, and I get degrees of freedom from the smaller sample. So yes, degrees of freedom would be 35. Is it on the table? No. So I'm going to use 30 instead. Oh, I'm sorry, 34. That would be the next one.
A situation like this where the degree of freedom is not on the chart, would you always go to the next one down, I guess? Or would you go back to 36?
Up.
Off the chart for the lower numbers.
That's correct. Go to my next lower number.
But we're still going to use 36 people?
That's correct.
Alright.
Right. So, Katie, you got that critical value?
2.032.
Kidding. Thank you.
Sorry,
Thank
now
you.
screwed me up with these numbers.
Yeah, we just do up the numbers here.
Yeah,
Huh?
1.691.
1.691 is correct. Katie, we're going to use positive or negative? Positive. So we're talking about alpha being 0.05, one tail.
Is it ever going to be two tails?
No,
Okay.
not in this chapter. Confidence intervals are always two-tailed. Hypothesis testing is one-tailed. For us. Okay. All right. So So we know we're using T because we're talking about averages. We're using the degrees of freedom of the smaller sample. In this case, it's not exactly on the table, so we go just a little bit less. For sample size, we end up with this number. It's our critical value. Sarah, what's next?
Find the test value.
Test value. So Sarah, can you tell me the formula I'm going to use for the test value?
Is it T equals x bar 1 minus x bar 2 divided by the square root of S1 to standard deviation 2, or 1 squared. Did I
Okay,
say that
S1
right?
squared.
Okay. Divided by N1 plus S2 squared divided by N2.
Okay, there we go. So this is the T for the difference of two averages. So we're going to say this is going to be 30 minus 25 on top. Then on the bottom we have square root of 10 squared divided by 40 plus 8 squared divided by 36 gives us that number right there. So then our test value is 5 divided by that, giving us a test value of 2.417. All right. 2.417. Any question about getting that number? Okay. So, Ta, what do we do with that number?
We reject the null
Okay, we're going to reject the null, and why are we going to do that?
because the number is in rejection region.
That's correct. This number here, which is the test value, is in the rejection region, so we reject the null hypothesis. Okay. So, Joseph, what does that tell us?
That tells us that we were able to prove the alternative.
Okay. Okay, so we're able to prove the alternative, but what does that actually mean?
That means that the mean time spent preparing meals for ag business is greater than the mean time spent preparing meals in the welding.
That's correct. Okay, the average time that ag business students spend preparing their meals, the average is greater than that of the welding students. Okay? That's what we proved.
Do we have to go through the list of conclusion?
So yeah, then we would say with 95% confidence there is evidence that the population mean of the time spent preparing meals for ag business students is greater than the population mean for the welding. Okay. What have we not covered?
We talked about last time about sometimes we don't actually have the wrong answer, and we just say yes or no.
Yeah. So when I say short answer, it's really hard for me to say that you could just say yes. Because if I ask you for the short answer, I'm probably also going to ask you for the long answer, okay? Unless we have a situation where we do not reject the null hypothesis. Because if we do not reject the null hypothesis, then it's really not important for us to do the long answer in that situation. Okay? Katie, what's the short answer if I do not reject the null hypothesis?
No decision.
No decision, so we don't know anything. So why go through the whole thing if we don't know anything, right? Okay. What else have we not covered? I should do this in all my classes. When it's time for test review, I go through it and I say, okay, what haven't I talked about? And then that forces you to go through and figure out what I have talked about. What's missing? Yes, I even printed it out and I handed it out to you. Down in black and white. That? What have I not covered that's on here? Mean of the differences, or the matched pairs problem. Okay? We've not done a matched pairs problem. There's a reason, okay? Because if we do a matched pairs problem, we have to go through and do all the differences and find the mean, the standard deviation, all that stuff. So you need to understand the matched pairs problem, but we're not going to go through that whole thing in terms of all that stuff. Okay? It's probably enough for you to have to deal with what we're doing.
So it's not going to be unjust?
I wouldn't go that far. Right? Remember that I said you have certain parts of the problem
Yeah.
where I say you do those particular parts. I'm not going to give you an entire matched pairs problem.
Okay.
So that's one of my little secrets that's out now. Okay, I'm not going to give you a matched pairs problem to do the whole thing on the test. Okay. But that's it. Okay, that's all. I think that's enough for us to say that we're going to do all that. Make that work. So, yeah. Enjoy your weekend. And I will plan to see you on Wednesday for the exam, unless you decide you want to take it to the math lab. And then
You want me to stop this? The camera?
yes, please.